Momentum of explosions. To work out the momentum of an object, you multiply its mass in kilograms by its velocity in meters per second. The units of momentum are kilograms meters per second. Because velocity is a vector and it's involved in the calculation of momentum, that means momentum will also be a vector. A vector has both size and direction. When you're working out the momentum of an object, you need to assign one direction as positive and the opposite direction as negative. For example, you could say that if an object moves to the right, it has a positive momentum, and if an object moves to the left, it has a negative momentum. I'll show you what I mean by using the law of conservation of momentum when applied to explosions. All that the law of conservation means is that the total momentum before an event equals the total momentum after the event. In this case, the event is an explosion. Remember, the law of conservation of momentum only applies to a closed system where no energy can be lost or gained and no external forces act. In real life, however, external forces such as friction always act. But this law does let us work out roughly what will happen. Let's look at this real life example of a gun being fired.
Alright, cock back that hammer. Here we go.
Please notice the information in yellow, blue and red that I've put at the top of the screen. This is typical for this type of question, where you're given 3 pieces of information and asked to work out the 4th. When a gun is fired, there's an explosion in the chamber that sends the bullet flying forward and the gun recoils backward. The law of conservation of momentum tells us that the total momentum before the explosion equals the total momentum after the explosion. The total momentum before the explosion is the momentum of the bullet before the explosion added to the momentum of the gun before the explosion. Since neither the bullet nor the gun are moving before the explosion, then the total momentum before the explosion is 0. After the gun is fired, the bullet clearly has momentum to the right. So, how is it possible that the total momentum after the explosion equals 0 like it was before the explosion? Well, let's not forget the momentum of the gun, which is going to recoil and move to the left. As I said before, momentum is a vector, which has both size and direction. So we need to assign one direction as positive and the opposite direction as negative. In this example, I'll say anything moving to the right has positive momentum, and anything moving to the left has negative momentum. To work out the total momentum after the explosion, we need to add the positive momentum of the bullet to the negative momentum of the gun. If you add a negative number, it means you take it away. So the total momentum after the explosion equals the momentum of the bullet moving to the right. Take away the momentum of the gun recoiling to the left. Now, since the total momentum after the explosion has to equal 0, that means that the momentum of the gun recoiling to the left must be the same size as the momentum of the bullet moving to the right, but opposite in direction. That's probably the hardest bit to understand. So, the mass of the gun times by the velocity of the gun recoiling to the left equals the mass of the bullet times by the velocity of the bullet moving to the right. So if we know the gun is 2 kilograms in mass, then that's 2 kilograms times by the velocity of the gun recoiling to the left. If we know the bullet is 10 grams, which is 0.01 kilograms, and it travels at a velocity of 200 meters per second to the right, then the momentum of the bullet is 0.01 kilograms times by 200 meters per second, which equals 2 kilograms meters per second to the right. We can then rearrange the equation to find the velocity of the gun recoiling to the left. So that will be 2 kilograms meters per second divided by 2 kilograms, which equals 1 meter per second to the left. Now, if we stop and think about the velocity of the gun compared to the velocity of the bullet, we'll realise that the velocity of the gun is 200 times smaller than the velocity of the bullet. And that's because the mass of the gun is 200 times bigger than the mass of the bullet. That's how the momentum of the gun and the bullet are the same size. Do you see? That's a high level observation, but remember, this whole video is for higher tier only.
Yeah.
Let's look at this next example to help you get the hang of it. From the last example, you now understand that if the total momentum before the explosion is 0, then after the explosion the momentum is also 0, which means the momentum of the object going to the left must be the same size as the momentum of the other object going to the right. So we'll just jump straight to that step. I've left the whole derivation on the screen though, so you can pause it if you want to have a look. Pause the video and try and do it first before I reveal the answer if you want. And here's the answer. Here's another example to look at.
Put some buckshot in there and then shoot it one-handed. That's a point. Oh. What?
It's alright, I didn't need front teeth.
Pause the video and try and do it first before I reveal the answer if you want. And here's the answer. Here's another example to look at.
A little sympathetic detonation there. You got that on video. Oh, I got that on video.
Pause the video and try and do it first before I reveal the answer if you want. And here's the answer. And here's the final example. Pause the video and give it a go. And here's the answer. Well, I hope that's helped you understand about the law of conservation of momentum during an explosion. Subscribe to the channel if you haven't already. These videos do take a while to make, so your support would be champion. Let me know in the comments below if there's a particular video you'd like made, and I'll make it happen. Work hard, be nice, stay safe, and bye for now.